Welcome, curious minds, to the deep dive. Okay, imagine this for a second. What if the universe, what if the basic rules we thought we knew, things like gravity, even time itself, were, well, fundamentally different?
It's a wild thought, isn't it? Like maybe the universe isn't expanding the way we picture it. Maybe dark matter isn't quite the full story.
Exactly. These aren't just, fun what-ifs. They strike right at the heart of how we understand reality. And it feels like we're genuinely on the verge of something huge.
We really could be. The potential for discovery right now is immense. It could mean rewriting a lot of cosmic textbooks.
Absolutely. So today we're diving deep into some really revolutionary concepts that are reshaping cosmology. You've shared some great sources, articles, research papers focusing on the incredible Vera C. Rubin Observatory and this pretty bold new idea called motion theory.
That's right.
Our mission really is to pull out the key insights, the most important bits from all this material, give you a shortcut basically to understanding a potential massive shift in how we see the universe. We'll explore how the Rubin Observatory is perfectly placed to actually test these radical ideas. Expect some surprising facts and definitely some mind-bending concepts.
And to really set the stage, we have to start with the person the observatory is named after, Vera Rubin, a true pioneer. Her work, her initial discoveries about how galaxies rotate, really kicked off one of the biggest puzzles in cosmology.
Right, that was almost 50 years ago.
Yeah.
Her observations were the key. She found galaxies rotating way too fast out at their edges. It just didn't make sense for the visible matter.
Yeah, it's like if you imagine a spinning merry-go-round, the stuff on the outside should be moving slower or flying off, but it wasn't. It was holding together somehow.
Which led directly to the idea of dark matter, right? This unseen mass providing the extra gravity needed.
Exactly. And for decades, that's been the standard picture. Invisible dark matter halos around galaxies, holding them together. It's, a cornerstone of the standard cosmological model.
It's the cosmic scaffolding we've built our understanding on.
Yeah.
But what if that scaffolding isn't the whole picture, and that's where this motion theory comes in? It's a real challenger.
It really is. It doesn't just nibble at the edges. It proposes a completely different mechanism. It suggests those rotation curves Vera Rubin saw aren't about extra gravity from dark matter.
Okay, so what are they then, according to this theory?
They're seen as manifestations of something called structured motion synchronization. It's a fundamental shift.
Structured motion synchronization. That sounds complex.
It is, but the core idea is that gravity itself is different. Motion theory reimagines it. It's not a force carried by particles in the way we usually think.
Okay.
Instead, picture it as like a tendency towards order, a convergence of structured motion towards areas of higher synchronization density. Things naturally fall into step, into rhythm on a cosmic scale.
Wow. Okay, so gravity isn't a pull. It's more like joining a dance.
That's a decent analogy, yeah. And the amazing thing is, this perspective naturally explains something called the radial acceleration relation, or RAR.
Ah, yes, the RAR. That's the observation where the visible matter in a galaxy seems to perfectly predict its rotation speed without needing to calculate dark matter separately, right? Which always felt a bit coincidental under the standard model.
Exactly. It seemed like dark matter knew exactly how much normal matter there was. Motion theory says it's not a coincidence. It's a direct outcome of this motion synchronization. The visible matter dictates the synchronization pattern.
That is a profoundly different way of looking at things. So how does the Rubin Observatory fit in? How can it test something this fundamental?
Well, Rubin is going to map the sky with unprecedented depth and breadth. It's going to gather data on billions of galaxies. It can meticulously check if these galaxy rotation curves universally follow the patterns predicted by synchronization.
Or if we still need those dark matter halos to make the observations fit.
Precisely. It's going to provide a massive data set to either strongly support this new idea or, reinforce the standard dark matter picture. It's a crucial test.
Okay, let's scale up. You mentioned synchronization. What about on really large scales? I read something about cosmic filaments.
Yes, this is fascinating. Recent observations, some really mind-boggling stuff, show coherence on scales we just didn't expect. We're talking about filaments of galaxies in the cosmic web, stretching hundreds of millions of light years.
Okay.
And they seem to be rotating, like giant cosmic corkscrews. The level of coordination across such vast distances is, It's hard to explain with just gravity as we know it.
Rotating filaments hundreds of millions of light years across. That's wow.
Right. Now, motion theory looks at this and says, see, these are huge synchronized motion structures. They're not just random collections pulled together by gravity. They're remnants of fundamental early universe rhythms playing out on enormous scales.
So it fits the pattern. And wasn't there something from the James Webb Space Telescope, the JWST, that also pointed towards unexpected coherence?
Yes, absolutely. JWST data showed a really puzzling bias. On a cosmic scale, spiral galaxies seem to preferentially spin in one direction more than the other.
Like more left-handed spirals than right-handed ones or something like that?
Essentially, yes. Way more than you'd expect by chance. It's like flipping a cosmic coin billions of times and getting heads way too often. It suggests either some observational effect we don't understand or, as motion theory would suggest, an intrinsic synchronization built into how galaxies form across these vast distances, a shared cosmic spin.
And Rubin, with its huge survey, can map out the spins of billions of galaxies to see if this bias is real and universal.
Exactly. Rubin can investigate these alignment phenomena like never before. It'll give us critical data to see if this large-scale synchronization is really happening or if there's another explanation for the JWST results.
Okay, so we've got galaxy rotation, large-scale filaments.
Yeah.
What about closer to home, like the satellite galaxies around our own Milky Way? I remember reading those are a bit of a puzzle, too.
They absolutely are. Observations show that the small satellite galaxies orbiting big ones, like the Milky Way and Andromeda, they don't just buzz around randomly like bees around a hive, which is what simulations based on dark matter predict.
Right. They tend to line up in thin planes, don't they? And often orbit in the same direction within that plane.
Precisely. It's called the plane of satellites problem. It's a stark contradiction to standard lambda CDM cosmological simulations. Those simulations predict a much more spherical, random distribution.
So how does motion theory handle this? Does synchronization explain the planes?
Well, yes, potentially. Motion theory reframes it. Instead of a problem, these alignments become a natural consequence of motion synchronization. The idea is that these smaller satellite galaxies are sort of caught in the larger rhythmic motion field of the host galaxy.
Like leaves swept along in a current.
That's a good way to think about it, yeah. They inherit synchronized orbital patterns. It explains the coherence, the shared direction, the planar structure, without needing complex, fine-tuned initial conditions.
And Rubin, again, its job is to see how common these planes are everywhere else.
You got it. Rubin's deep, wide view will allow us to survey thousands of galactic systems. We can finally determine if these synchronized satellite arrangements are the norm or just a local fluke. If they're common, it's another strong point for motion theory.
Okay, this is all fascinating, but now let's tackle something even more fundamental. Redshift, expansion, time itself. The traditional view is pretty clear, right? Redshift means the universe is expanding.
Right. Light from distant galaxies gets stretched as space itself expands, shifting it towards the red end of the spectrum. The further away something is, the faster it recedes, the more redshifted its light. This implies we're seeing distant objects as they were long ago.
Looking back in time, essentially.
Exactly. But motion theory, well, it offers a radically different interpretation.
Uh-oh. I have a feeling this is going to bend my brain again.
It might. Instead of universal expansion causing redshift, motion theory proposes it's due to a gradual loss of synchronization between the distant source and us, the observer.
Loss of synchronization. How does that cause redshift?
Imagine light, or any signal, traveling through these universal motion fields. Over vast cosmic distances, the inherent rhythm or synchronization between the emitting object and the receiving observer degrades slightly. It's like the signal gets subtly out of step.
Okay.
This out-of-stepness, the synchronization decay, manifests as a redshift. The further the light travels, the greater the potential decay, the larger the observed redshift. It mimics expansion, but the cause is different.
So the universe might not actually be expanding. The redshift is just an effect of light losing its rhythm over distance.
That's the core proposal. It's a big one, obviously, but think about what it implies.
It would certainly explain those weirdly mature galaxies JWST found at very high redshifts, wouldn't it? The ones that look too old for how early they supposedly are in an expanding universe timeline.
Precisely. Those impossibly early massive galaxies are a real headache for the standard model. You have to really tweak galaxy formation theories to get them that big that fast.
What in motion theory?
In motion theory, they aren't ancient snapshots from a baby universe. They're potentially contemporary mature structures that exist now. We're just seeing them through this veil of synchronization decay, which makes them appear very distant and thus early because of the high redshift.
So the redshift tells us about synchronization loss, not necessarily distance implies time in the past.
Exactly. It resolves the tension of those mature galaxies instantly. The universe might be filled with structures that are all, in a sense, existing now, just viewed through different degrees of synchronization lag.
Mind blown. Okay, Rubin. How does Rubin test this? This seems like the biggest claim yet.
Rubin will create the largest, most detailed 3D map of the universe ever. It will measure redshifts, distances using things like type Ia supernovae, and how structures cluster on vast scales. It can meticulously check if the relationships between distance, redshift, and brightness perfectly match the predictions of an expanding universe.
Or if there are subtle systematic anomalies that align better with this synchronization decay model.
Precisely. Are the expansion rates consistent across different methods and distances? Or do we see discrepancies that hint at something else, like synchronization effects, influencing our measurements? Rubin's data will be definitive.
Speaking of discrepancies, that brings us to the Hubble tension, or the H-naught problem. This major headache in cosmology, where different ways of measuring the universe's current expansion rate give different answers.
Right. Measurements from the early universe, like the cosmic microwave background, suggest one expansion rate. Measurements from the local universe, using supernovae and Cepheid stars, suggest a slightly faster rate, and they just don't agree within their error bars. It's significant tension.
Does motion theory offer a way out here?
It offers possibilities, certainly. For example, remember that weird preferred spin direction for galaxies seen by JWST?
Yeah.
If that's a real physical effect related to synchronization, it might subtly affect how we calibrate our standard candles, like supernovae, which we use to measure cosmic distances. If our rulers are slightly off because of these underlying synchronization patterns,
then our measurements of the expansion rate could be skewed, potentially resolving the tension.
it's a possibility that needs exploring. Motion theory suggests these fundamental synchronization effects might ripple through many of our cosmological measurements in ways we haven't accounted for.
And again, Rubin's massive dataset measuring countless supernovae, mapping galaxy clustering in minute detail, is key to investigating this.
Absolutely. Rubin will provide the statistical power to test these calibration-related ideas, to see if anomalies linked to synchronization could explain the H-naught tension, or perhaps reveal even deeper issues. It will either clarify things or potentially make the puzzle even more complex.
Which is exciting either way, really. So it all comes down to this. The Vera Rubin Observatory is poised as the ultimate reality check for motion theory.
That's a great way to put it. Its sheer observational power scanning the entire southern sky repeatedly for 10 years is unprecedented. It will either find compelling evidence for the kind of synchronization and structured motion patterns predicted by motion theory,
or it will strongly reaffirm the standard model, cementing the roles of dark matter and cosmic expansion.
And whichever way it goes, it's a huge leap forward for our understanding. If motion theory gains ground, we're talking about fundamentally rethinking gravity, light, time, the whole cosmic history.
Okay, so boiling it down, as Rubin starts its survey, what are the key signatures we should be watching for if motion theory is onto something big?
You'd look for confirmation of widespread synchronization phenomena. Things like, are galaxy rotation curves universally explainable by visible matter via the RAR without needing dark matter? Do we see coherent rotation in cosmic filaments everywhere we look? Are those planar alignments of satellite galaxies common?
And do the redshift distance relationships show subtle deviations from pure expansion, especially at large distances? Are there unexpected patterns in galaxy orientations or clustering?
Exactly. If Rubin consistently finds these kinds of patterns that are naturally explained by structured motion and synchronization but are awkward or unexpected in the standard model, then it builds a very strong case.
Conversely, if Rubin finds that dark matter halos are definitely needed, that large-scale structures behave randomly as expected from gravity alone, and that redshift perfectly tracks expansion,
then that would be powerful evidence confirming our current physics, solidifying the standard cosmological model.
So the Vera Rubin Observatory is embarking on this incredible journey. It's really set up to answer this fundamental question. Is the universe this grand cosmic symphony of synchronized motion? Or is it governed primarily by dark matter and expanding spacetime, as we've thought?
And no matter the answer, the insights we gain from Rubin are going to be transformative. They will absolutely shape the future of cosmology.
So as we wrap up this deep dive, Motion theory and the power of the Rubin Observatory really invite you, the listener, to think about the universe differently. Consider a cosmos where everything, from the smallest spin to the largest structures, isn't just about matter and gravity. It's about intricate, synchronized patterns of motion.
What if the deepest language of the universe isn't just physics equations as we write them now, but something more like an elegant, evolving dance of motion synchronization? How would that change your perspective on everything?